Hi students! So we finally made it to the end of Geometry A. So this is the very last lesson of our course. And we're going to be talking about properties of kites and trapezoids in this lesson. And we've actually just finished up talking about all the other kind of special quadrilaterals. We talked about rectangles, rhombuses, squares, parallelograms, things like that. And so now we're going to focus on the other members of that family tree, the kites and the trapezoids. So as part of our discussion on the family tree, on that hierarchy, we talked about what a kite was. And so I actually mentioned this definition earlier on. A kite is a quadrilateral with at least two pair of congruent consecutive sides. Okay, that means sides that are next to each other that are equal. So like for instance, this is what a typical kite would look like. And you can see that these two sides are marked congruent. And also, these two sides are marked congruent. So they're consecutive because they're next to each other. And that's what we mean by a kite. So which came first, I don't know, whether it's the one that you fly in the air and then this figure looked like a kite, so they called it a kite, or whether the things we fly up in the air look like the geometric figure that's a kite, and that's where it got its name. But anyway, when we think of the typical kite, we think of something that looks like this. Now, when we looked at all those other special quadrilaterals, we were able to say the first part of the theorems were that they were parallelograms. Well, a kite is not a parallelogram. So it does not have all those properties that the parallelograms have, that also were shared with the rectangle and the rhombus and the square. But it does have some special properties that we're going to detail here in this theorem. So if a quadrilateral is a kite, then number one, so if quadrilateral is a kite, then its diagonals are perpendicular. Well, that sounds familiar. That was what was true of a rhombus. And so then basically where it got it from was from its parent in the family tree, the kite. So the kite had the perpendicular diagonals. So over here in my drawing, these diagonals make 90 degrees. The rhombus got it, and then the square got it actually from the rhombus, which got it from the kite. So just as we pass traits down in families, this is a trait of a kite, perpendicular diagonals, and it's been passed on to all of those in the hierarchy. Now another property of a kite is if a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. Now, when it says exactly one pair of opposite angles, well, how do you know which pair? Well, it turns out it's the pair where the two non-equal sides, I guess, well, I guess here's how we could say this. The two angles where the equal sides meet are actually called ends. So like this would be called an end here, and this would be called an end. So it's not those angles, it's the non-end angles. But here's an even easier way to remember which angles are congruent and to remember lots of other properties about a kite that is true. And that's this, that if you were to draw on the diagonal through the ends here, so that means where the two equal sides meet, if you were to draw a diagonal through those, that diagonal would actually be a symmetry line. So what a symmetry line is it's basically like a mirror. And so anything on one side has a reflection image or something that's exactly equal to, congruent to it on the other side. So if we know that diagonal that goes to the ends is a symmetry line, then we know that these two angles that we were just talking about that were supposed to be congruent, angle B in this case and angle D, they have to be congruent because they're mirror images of each other. But you know, it also actually gives us a lot of other properties that are true too. In fact, it kind of guarantees the fact that these sides are equal, which we knew already, it being a kite. And then it also means that these little angles on either side of this bisector are equal in measure. So that means the angles at the ends of the kite are bisected by this symmetry line. So by going a little beyond what that theorem says and actually showing that diagonal through the ends is a symmetry line, which we could prove using triangle congruence, but then we can get a lot more information out of a kite by just knowing that fact. So let's see if we can put these theorems together in example 1. So it says that Lucy is making a kite with the dimensions shown. To complete the kite, she needs a rod to place along KL. She has a rod that is 36 centimeters long. About how much of the rod will she have left after cutting the last one? Okay, first of all, let's take a look at this drawing. And what we want to find is we want to find the length of KL. That's what we want to find by the time we're done. Well, notice this measurement up here. So we have this measurement that says that all the way across that kite is 30 centimeters. And what that means is that each piece of diagonal JM is 15. And here's the reason. Because we said that that line, in fact I highlighted it as KL, we said that that diagonal is a symmetry line. And so if it's a symmetry line, it actually cuts that diagonal into equal parts. So each of those is 15 centimeters. And when we draw on the diagonals for a kite, we actually split it into 4 right triangles. So one of those right triangles would be this triangle that I'm highlighting right here. And if we have a right triangle and we know 2 parts of it, which we do, we can the third part. And so actually I'm going to call this third part A, and I'm going to take that little right triangle, redraw it over here, and I'm going to look for the length of A. Because then if I could find that, and let's say I called this length down here B, then that diagonal KL would be equal to A plus B. So I find those 2 lengths, add them together, that'll give me that whole diagonal. And so I know that in this little right triangle here, I have a leg that's 15 and a hypotenuse that's 18. So I can use Pythagorean's theorem like this. A squared plus 15 squared equals 18 squared. And so A squared plus 225 is equal to 324, which is what 18 squared is. Well, if I subtracted 225 from both sides, it would leave me with A squared equals 99. And so if I were to take the square root of both sides, and because this is one of those real life problems where it's really not going to do me a lot of good to have answers that have like radicals in them, then I'm going to go ahead and use my calculator to approximate the square root of 99, and it is about, so A is approximately 9.94987. So we're going to round it to about 9.95 centimeters. So that piece is about 9.95 centimeters. Now what about the other one? So if I wanted to find the length, let's say I called this other part B, there. So then I can use another right triangle in this picture. So I could identify, say, this right triangle right here. And that means I know 2 sides. I know one side is 15, that's a leg, and I know the hypotenuse is 27. So I could just go through that same process. 15 squared plus B squared equals 27 squared. 15 squared is 225 plus B squared equals, and 27 squared is 729. So I could subtract 225 from both sides, and that would leave me with B squared equals 504. And of course I want to take the square root of both sides then to find out what B is. And I'm going to go ahead and round this because, again, it's a real life problem. I really kind of need to know what that is in a decimal approximately. And so the square root of that 504 is about 22.45 centimeters. So here was the question. The question was, I have 36 centimeters. Well, Lucy, has 36 centimeters to use. See that, 36 centimeters? Does she have enough? Well, if I take these 2 lengths, A, which was 9.95, and B, which is 22.45, they add up to 32.4 centimeters. So I have enough because all I needed was 32.4 centimeters and I've got 36. So my answer is, will she have enough? Yes. The answer is yes, she has enough. Let's go ahead and look at another example. All right, so in this example, we're really going to see the power of that theorem, which we sort of adapted and kind of expanded on a little bit to say that the diagonal through the ends of the kite is a symmetry line. And so we're asked in this drawing to find all these measurements, only given a couple. So they want us to find every one of these angles in this drawing. And so I know that I just identified these ends, A and C. And so that means that this line that's cutting through those right here, that is a symmetry line. That's the one. And here are some other measurements I know. I know that the measure of angle DAB, so DAB is this whole angle down here. This whole angle down here is 54 degrees. And then I also know that CDF, so let's see where CDF, CDF, that's this angle right here, angle 5, is 52 degrees. And that's all that they give me, and they want me to find all the rest of the measures. Well, so we know that this line is a symmetry line. A symmetry line will cut segments into equal parts, cut angles into equal parts, and so we actually know that these two angles down here at this end, 7 and 8, are congruent, and we know that 3 and 4 up here are congruent. So I marked that. And I actually also know that this whole angle, angle B, this entire thing right here, is the same as the angle D over there, because those are reflection images over the mirror or the symmetry line. And so, other than that, the final thing that I know about the diagonals of a kite is they are perpendicular. So I actually know that all these angles here in the center are 90 degrees. So at least I have a start. I know that these are 90 in the center. So I'm going to go ahead and label those, and you can label them, try to make it big enough so you could just label them right on the drawing. So all my angles in the center are 90 degrees. So I've got those. And now let's see what else we can find. So even this angle, it's not even labeled, but that one's 90 as well. So let's say we wanted to find the measure of angle 4. Well, the measure of angle 4, that angle right there, that angle is actually in a right triangle, which I'm going to highlight right here. And so in that right triangle, I already know the 90-degree angle. I know I have a 52-degree angle, and that means that this remaining angle must be 38 degrees. Because then that would give me a sum of 180 degrees in that yellow triangle. Well, then that means that angle 3 is also 38 degrees, because that line is a symmetry line. So whatever angle measure I have on one side, I'll have the identical measure on the other side. So that one's 38 degrees. Well, keeping that in mind, if angle 5 is 52, that means angle 2 must be 52 degrees. And what a lot of people do is they'll make the mistake to think then that means that angle 1 is 52 degrees. But remember, it's only one of the diagonals is a symmetry line. It's just the one that goes through the ends, or in other words, where the two equal sides meet. But I can actually find the measure of angle 1 by looking at a bigger triangle within this kite. So if you look at, and I know that this angle down here actually has to be 27 degrees. Now why is it? Because the whole angle is 54, meaning that each one of these angles has to be 27 degrees. So I could actually find out the measure of angle 1 by knowing that I have a 27-degree angle, a 38-degree angle. I have part of this angle is 52, so I could figure out what the rest of that is. Or I could even just look at this triangle right here. Just say, okay, I got another right triangle, and now I know that I have a 90 and a 27, and that leaves this angle right here to be the rest of 180 degrees if I subtract 90 and I subtract 27, which would actually leave me with 63 degrees. So that one's 63 degrees. Go on the other side, angle 6 will also have to be 63 degrees. And now we have found each and every angle in this kite. So using properties we know about the triangle sum, about the fact that the diagonals are perpendicular and that AC is that symmetry diagonal, we can actually find all of these angles just given those two initial angles. So that's enough about kites for right now. Let's go ahead and take a look at the next special kind of quadrilateral, and that is a trapezoid. So a trapezoid is a quadrilateral with at least one pair of parallel sides. So those parallel sides, we actually call those bases. So each of the parallel sides is called a base. So in this drawing, these are the bases. They're the sides that are parallel. And the non-parallel sides, we actually call them legs. So we use legs to describe a lot of things, like legs are sides of right triangles. But they, in the case of a trapezoid, are the non-base sides. We call those legs. Okay, let's go ahead and turn the page. Now, base angles of a trapezoid are two consecutive angles whose common side is a base. And in this drawing here, I have an example of base angles. So this is a base here, right here. And so these would be base angles. And this is a base up here. And these two would be base angles. Now the reason why I'm actually marking them congruent is because if I want to talk about the properties of an isosceles trapezoid, an isosceles trapezoid is a trapezoid where the legs of the trapezoid are congruent, and what that does is it causes the base angles, both pair, to be congruent. And so that's an isosceles trapezoid. And if something is an isosceles trapezoid, then these things are true about it. First of all, if a quadrilateral is an isosceles trapezoid, then each pair of base angles are congruent. Well, that's what I just alluded to here. This fact I just marked on this drawing. So your base angles will be congruent, much like in an isosceles triangle. The base angles were congruent. In an isosceles trapezoid, the base angles are congruent. Next, if a trapezoid has one pair of congruent base angles, then the trapezoid is isosceles. So this is actually a theorem that you can use in a trapezoid to make sure and prove that it is in fact isosceles. So you have a trapezoid and a pair of the base angles are equal. That actually means that the entire trapezoid has to be isosceles. And next, a trapezoid is isosceles if and only if its diagonals are congruent. And so the only way that something can be an isosceles trapezoid is if its diagonals are congruent and vice versa. So if the diagonals are congruent, it's got to be isosceles. If it's isosceles, the diagonals are congruent. Now you may remember that the rectangle, it had congruent diagonals, and that's where it got it from. And then it actually passed it also on down to the square. So it originated, that trait, in the isosceles trapezoid, and it was passed on to the rectangle and down to the square as well. So those are all the important properties of isosceles trapezoids. Now the first example we're going to look at asks us to find the measure of angle A. So here's angle A. And we've got a trapezoid and it's isosceles. So we've got these two sides equal, these sides are parallel, and we want to find the measure of angle A. Well, first of all, I know that angle A must be congruent to angle B if this is an isosceles trapezoid. And so if I could find angle B, angle A would be the same thing. Well, you may remember that because we have a pair of parallel sides, these two angles, C and B, are actually same side interior angles, and because the lines are parallel, these have to add up to 180 degrees. And so what that means is the measure of angle B has to be 80 degrees. So B must be 80, and that means that angle A must be 80 as well. So we've got the measure of angle A by finding B, and we used the fact that we have parallel lines and same side interior angles that would have to be supplementary. So angle A is 80 degrees. How about example B? So in example B, we want to find the length of FB. And here are the parts that were given to us. We know that KB, so that means from here to here, this part right there, is 21.9. And we know that the length from M to F, so that means this whole entire thing from here all the way down to M, that length right there is a total of 32.7. Well, remember the diagonals are supposed to be equal. So if the whole diagonal FM is the same as diagonal KJ, then they're both 32.7. And that means this little piece right here from J to M, okay, from J to M, I can find from J to B would have to be 32.7 minus 21.9. And that leaves me with 10.8. And if JB is 10.8, then FB is also 10.8. So that was basically applying the fact that diagonals have to be congruent in an isosceles trapezoid. Let's go ahead and turn the page. Here's one more example that applies to isosceles trapezoids. So I want to find a value of A, the variable A, that would ensure that this figure, PQRS, is isosceles. So in order to be isosceles, we know that the legs have to be congruent. That's first of all. We don't have any way to prove that. But so they would have to be congruent, and the base angles would have to be congruent, both pair, which means angle P and angle S would have to be congruent. So that's what I'm going to do. I'm going to set angle P equal to angle S and find out the value that would actually make them equal. So angle P is A squared plus 27. Angle S is 2A squared minus 54. And I'm going to go ahead and solve that. First thing I'm going to do is subtract A squared from both sides. And that actually leaves me with just A squared minus 54 on this side. So I'm going to add 54 to both sides, and that makes 27 plus 54. That's equal to 81. So A squared is equal to 81. I can take the square root of both sides, and because I'm dealing with square root, it technically could be positive or negative. So A must be plus or minus 9. And so it could be positive 9, it could be negative 9, either one, but both values, these are most likely the most common one given would be the positive 9, but both of those would, when I plug them into those angles, give me equal angles and make this isosceles. All right, so finally, so this is sort of ceremonial. This is our very last theorem of geometry A. So, and this theorem is going to sound familiar because it hasn't been too long ago since we studied mid-segments of triangles. So we're going to be looking at a mid-segment of a trapezoid. And just like the mid-segment of a triangle, a mid-segment of a trapezoid connects midpoints of two sides of a trapezoid. So I have two midpoints here on this trapezoid. And I can tell by the markings on either side that they're midpoints. And so that segment connecting them is a midsegment. And this theorem details the properties of a midsegment of a trapezoid. And it says this: the midsegment of a trapezoid is parallel to each base. So it's saying that the midsegment is parallel to both of the bases, and its length is 1/2 the sum of the lengths of the bases. And another way to say that is it's the average of the base. So it makes sense that the mid-segment would have to be the midway between, in terms of length, the two bases. And the mid point between two numbers is always the average. So another way to find the length of a midsegment is just to average the two bases. Okay, so say in this example, for A, I wanted to find the length of EF. So here's EF. I want to find the length of that midsegment. Okay, so what we just learned is that the midsegment is 1/2 the sum of the length of the bases, or another way to say that is the average of the bases. So I could look at it like this and say that EF is equal to 1/2 the sum of the bases, which are 13.5 and 8. Okay, or I could think about it like this. I could think about it just averaging the two bases. So you average two things by adding them up and dividing by 2. And we're going to get the same thing for this. So either way we decide to do it, we're going to find out that that midsegment's length is 10.75. So the length right there is 10.75. So if you're given the two bases, all you have to do to get that midsegment is to average them or find the half of their sum. Now what about in this next example? So this time, they already gave us the mid-segment. They want us to find one of the bases. So they want to know the length of base EH. Well, I could use this formula, this average of the bases, or 1/2 the sum of the bases, but I don't know one of the bases. So what that's going to do is set up more complicated equations than I'd probably like to deal with. So instead, what you can think about is this: if that segment XY is the mid segment, then it's halfway between the two bases. Well, if you can figure out how far it is away from the one base, well, it's got to be the same distance away from the other base. So if you think about these bases and what's going on here, I had a base that was 25, and now the mid-segment, so I've gone halfway through the figure, and it is now 16.5, and so that means that it must have gone down by 8.5 units. So if that trend were going to continue, which it should if that's the mid-segment or the midpoint of the figure, and I went down another 8.5, I would be at 8 units. And so I'm going to say that I think the length of segment EH is 8. Now here's a way I could check it. I could take the two bases now that I know them. I know one of the bases is 8 and the other one is 25. I could add them together and divide by 2 or multiply a half by their sum and see if I don't get 16.5. Well, 8 plus 25 is 33, and if you divide 33 by 2, you get 16.5. And so it checks. Well, that actually does it for today's lesson. So if you had any trouble understanding any of the properties, be sure to make a note and bring it up when we see each other in class. See you then.